Hello, and thank you for joining us for this webinar surrounding the aerospace industry and the sensors used in such applications. Before we dive into the meat of this presentation, though, I'd like to take a moment to introduce FUTEK and our presenter. From the beginning, FUTEK has had a mentality of being solution-minded. And as you're soon going to learn, this mentality is completely necessary for aerospace applications. Whether it's using one of our standard models in a unique way, or designing and developing completely custom test and measurement products, we have built a reputation to say we've done a lot in this particular field. From our very first NASA project to the most recent, the famous Mars Rover, we've challenged ourselves to find solutions for these tough and demanding applications. And that's what our speaker, John Schnell, will lead you through. John is a senior application engineer here at FUTEK with over 30 years of test and measurement experience. He has personally forged many of our aerospace accounts and is extremely well versed in the challenges that this field presents. Today, John's going to lead you through the different certifications and compliances that are deemed necessary for manufacturing aerospace units, the different requirements between ground-based testing and flight-qualified testing, how FUTEK's miniature models have become a hot commodity when space, pun intended, gets tight, and through half a dozen illustrated applications so you can see how we provided multiple solutions for several complex applications. But before I turn this over to John, I'd like to remind you that we will have a Q&A session towards the end of this presentation. So please feel free to submit your questions at any time, and we'll try to get through as many as possible. Now, without further ado, John, the floor is yours.
Thank you, Natasha, for that introduction. Again, this is John Schnell. I'll be your presenter today. And first, let me thank everybody for joining us, taking time from your busy schedule to listen to our webinar. We hope to make this a very informative session today with significant takeaways from our webinar. As far as compliance for aerospace, it's an extremely important issue. As everyone is aware, the aerospace industry is probably the most demanding industry that we are associated with. Just to give you some background on FUTEK and our capability in this regard, we are compliant to AS 9100-2009. This is the standardized quality management system for the aerospace industry, and it certainly is something that's critical in making certain that we do everything correctly to meet the high demands of the aerospace industry. We also have trained technicians that allow us to conform and support to J Standard 001. This is the Space Applications Electronic Hardware Standard. The standard describes materials, methods, and verification criteria for the production of high-quality solder interconnections. The standard emphasizes process control and sets the industry's consensus requirements for a broad range of electronic products. Again, something that's extremely critical for the aerospace industry. We also have technicians who are trained to IPC A610 for soldering methods and techniques, and IPC A620, which is involved with the cables and connectors and interconnects between sensors and instrumentation, again, with a high degree of quality standards for aerospace. Some of the projects that FUTEK's been involved with recently that required these various standards and compliance to these standards has been the NASA ILIDS program, the MLS program, and the Raytheon project for satellite meteorology. I'd like just to take a little time to talk about FUTEK's certifications and our accreditations. First of all, very important, we are a U.S. manufacturer. We're based out of Irvine, California, and so I think it's extremely critical for these aerospace applications to deal with a local company. And everything as far as design effort, manufacturing, all done out of Irvine, California. As far as some of the pedigrees, and this becomes very important when you're making the assessment of working with a supplier, their credentials become very important. A lot of time and energy is spent on the part of manufacturers to achieve these objectives. In the case of FUTEK, we are 9001-2008 certified. We also, as far as our calibration is concerned, are certified to 17025-2005. And we also offer, which is extremely specific to aerospace, Z540 1994. What's important in making this decision in looking at vendors is these are requirements that most aerospace clientele are going to want to see. In summary, in making your vendor selections, I think it's very important to look at proximity. Local manufacturing and design effort is extremely important. And also, right up front, look at the certifications and accreditations. For aerospace, you're going to see, or you're going to need 9001, 17025, and Z540. So as you go down through your vendor evaluations, make certain that your vendors have these very specific certifications. Now that we've talked about what I refer to as the pedigree, we have an understanding of our potential supplier and what certifications they have, we want to get into the essence of today's discussion, and that is the testing aspect for the aerospace industry. And we typically break this down into two categories, what I refer to as the test and measurement or ground-based testing. That can also be referred to as GSE, ground support equipment, and also the flight qualified aspect, and both are very unique environments. In the case of ground-based testing, we're looking at applications that typically require material testing. We might be testing the actual material, or we might be testing a new component and looking for fatigue life. We might be looking at component testing where flight load simulation is occurring, such as a wing test, things of that nature. Structural dynamics, we could be looking at fuselage loads and unloads for stress testing, and also accelerated life testing, where we're going to take this component or this possible piece of this vehicle and run it through an accelerated life test. These are typical of what I refer to as ground-based testing, and many of you out there probably are already involved in that. Component testing is a big one for aircraft hydraulics and other components used on the vehicles. For both the test and measurement ground-based testing environment and the flight qualified environment, there are some significant aspects that factor in. Reliability is extremely important for any of these tests. Usually it's a significantly long test with tremendous expense associated with data collection. So high reliability is extremely important. Endurance at the same time. We've got to have sensors that are going to continue to work over possibly millions and millions of cycles, and so we also focus on high endurance for any of our sensors associated with aerospace testing. Multiple bridges, that's something that we're involved with on a regular basis. For most of the aerospace applications, and again for those of you involved in it, you're aware of this, where we are going to use a bridge for control and we're going to use a bridge for measurement. And that's something that is a bit unique to aerospace, but we're aware of that, and we do offer the capability for most of our sensors to be built with dual bridge capabilities for that control measurement requirement. And then last but not least, of course, great performance. And that's the other thing that's unique to aerospace. When you look at the breakdown of specifications, in the commercial world, we'll talk about accuracy and the components of accuracy being nonlinearity, hysteresis, repeatability. And then we handle the temperature errors as a separate entity. In many aerospace applications, the error budget is defined as a combined error of all those aspects: nonlinearity, hysteresis, repeatability, temperature effect on 0, temperature effect on span, and the aero budget will be given one total specification that you have to conform to. So understanding that and dealing with that is extremely important, which also requires you in many cases to tighten up on things like nonlinearity and hysteresis. If we move on to the next slide, where we continue on with this discussion, overload protection is something that we're very good with in many of our designs because we do EDM work in some of the machining processes. We can offer bidirectional overload stops in many of our designs. A lot of these applications, space is limited. You're dealing with devices that have to be used in very tight locations, and in many cases you can't change much in order to accommodate your sensor. So we're also very good at offering miniaturization in many of our designs, and those miniatures in some cases offer the overload stops, which ties into our standard product offering. We do address many of the aerospace applications with our standard products, and a lot of this has to do with the fact that when you look at our specifications, nonlinearity, hysteresis, repeatability, we utilize an endpoint methodology to determine our errors versus best fit straight line. So in many cases our standard products have performance capabilities that already meet the high demands of aerospace. In summarizing ground-based testing, and before we move on to flight qualified, I think it's important to note that the criteria for sensors for the ground-based testing extremely important because we're testing components that ultimately will fly and will be critical to that aircraft and the safety of that aircraft. So having high performance sensors perform these evaluations are extremely critical in that ground-based testing environment. Now if we move on to flight qualified, we'll see some of the same requirements that we saw for ground-based testing. I think what's uniquely different in the case of flight qualified work is we develop more of a partnership with the end user. Also, there's a key aspect here where there's more of a design effort associated with flight qualified. In many cases with flight qualified, we may not have a particular mill standard qualified unit off the shelf that we can offer. However, we have the capability to review those specifications, design to that, and that will then allow the end user to flight qualify his system or his product. But some of the things that come out in our flight qualified work that we're doing, for example, cryogenics, as again some of the audience can well imagine, a lot of these environments for space applications, we're going to see extreme temperatures, we're going to be working in a vacuum. Those are just standard environmental concerns or issues that we have to deal with. In the case of vacuum work, we have to work very closely with the end user to understand what outgassing requirements they may have. There's two methods that address that. In many cases, we'll ask the question about outgassing. They have to go back because they don't know and determine what that outgassing spec looks like. We then can make our design effort based on what their needs are. Compact, miniature, lightweight. Again, in many cases, we're dealing with environments where size, weight is very critical, and so we have, again, a demanding measurement application, yet we have very limited size. What you're looking at here on this slide is one of our more exciting projects that we've been involved with in the last few years, and that was the Mars Rover. We've actually got a multi-component solution on the current rover looking at both force and torque in the sampling process that's used. And as you can well imagine, it's a very extreme environment, and we were very successful at providing a viable solution with a very intimate partnership with the end user. Back to multiple bridges. Again, in many cases, we're dealing with a bridge for control and a bridge for measurement. So we try and maintain that capability across the product line. There's trade-offs between the last item, size, and multi-bridge. In many cases, you have to get very creative as far as your spacing to accommodate the additional strain gauges that we'll use to do that. Vibration, fatigue, and overload. Again, all environmental considerations that we have to look at. In the case of many flight qualified sensors, we're going to see extreme vibration environments, extreme cycles, possible overloads, as I already mentioned. For overload capability, because we EDM, we're able to offer that capability. That's something that a lot of the manufacturers don't have. And as far as vibration, we have a number of things that we can do as far as additional coatings, how we wire internally to secure our wires and our strain gauges to accommodate those high vibration applications. So in making an assessment for a potential supplier for a flight qualified solution, it's very important to find out what kind of history they have. Have they done other projects that are similar to yours? Do they have the expertise to be able to address the issues of cryogenics, high shock, high vibration, multiple bridges, those kind of things? And we've got a list of references and programs that we can bring to the table and show our client or a prospective client that here are the programs that we've been involved with. Here's the clientele, be it NASA, Raytheon, Lockheed, that we have partnered up with their technical team, and so we have quite an extensive legacy in providing custom, complex solutions to address these aerospace applications. As we begin our discussion on products and applications, I just wanted to take a moment and just introduce three flagship items that are only a small sample of our overall product line. The LTH through-hole series, which has been very instrumental in being customized or as a base platform for many aerospace applications. The LCM, which is the rod end series, again very common for a lot of structural testing environments, things of that nature. And the LAU family, which is commonly used for pedal force measurement in both commercial and aerospace applications. Now that we've covered the credential aspects of vendor selection, and we've talked a little bit about the importance of having that technical capability with your supplier to provide the right solutions, I'd like to get into more of the fun stuff, which is some of the applications that we've addressed over the years. Just a couple of comments I'd like to make before we get started. The information being presented here is generic in nature, and that's by design. A lot of these applications we're very limited on what we're allowed to discuss and or present, so we've had to sanitize some of the information to protect our client. And these are applications that we've provided successful solutions in the past. Something that's extremely important, and we stress with every new application, is to provide as much information to your potential supplier as you can. That allows us to get right into a correct design path without having to do any rework at the design level. Most of the time, a non-disclosure will be put in place that protects both of us, and I think the best thing to do for any complex effort that does have a proprietary feel to it is put an NDA in place. That allows both of us to share information back and forth, and it keeps everybody's information safe. If we look at this first application slide for the helicopter pedal force testing, and this is something that could be both ground test as well as flight qualified, and in many cases we start out as a ground test, or what I call test and measurement, in the early development phase, and then ultimately make our way into a flight qualified or flight test arena. In this specific application, the pitch of the tail rotor blades are adjustable by the pilot using an anti-torque pedal. This also provides directional control and allows the pilot to rotate the helicopter around the vertical axis. So as we can well imagine, that force measurement and that control is something that becomes very important, whether we're possibly developing a new structure or maybe we're testing the system for the first time. So the pedals change the pitch of the tail rotor blades. The anti-torque pedal controls both the direction and the pitch of the helicopter in flight. So again, something that's extremely critical, and we have to have something that obviously when you look at that environment, in many cases we have a situation where we can't change the physical appearance or configuration significantly because we want things to be as realistic for the pilot as possible. So if we look at the next slide, the helicopter pedal force testing, what we have is a very low profile device that gets attached to that pedal. This design was specifically targeted for these types of applications. It's got a very high spike resistance capability. As I mentioned, low profile, we want to keep that thing as realistic as possible for the pilot. It does have a nice slip resistant surface, extremely important to maintain control of the aircraft. And we also offer a broad range of capabilities or broad range of capacities from 50 pounds to 300 pounds. And again, this is a good example of something that starts out, we do have this as a standard product that has a nice niche in the commercial world, but take that standard product and with some design effort by our team in conjunction with the user's design team, possibly extended temperature applications, higher vibration capabilities, and so forth, we can build off that standard platform or that standard product platform and come up with a solution that meets the aerospace specifications. In our next application, which we're going to stay with the helicopter for a moment, we've got the helicopter joystick. And of course, I think as most of us know, I think the helicopter is probably one of the more complex devices to fly, at least talking to people who I know that fly for a living. Apparently it is one of the more difficult challenges. And when you look at the control for the joystick, knowing forces involved, and again, this could be a ground-based solution for new product development. It might possibly be in a simulator, or it could be for flight test. But we've got a great solution here with our joystick sensor, our little MAU300, that again, one of the objectives here is to provide, in this case, an XY force measurement, but we have to try and do that in a way that we don't modify the environment too much and yet provide good, reliable data for the X and Y movement or control that we're measuring. So in this case, we've got a nice solution. If we go to our next slide where we actually feature the sensor, we've got dual component, and that's another thing that FUTEK is very good at. We're very good at multi-component solutions. If you look on our website, you're going to see a category dedicated just to multi-component. And here again is a solution that possibly could be leveraged off of a standard product. By the time you add modifications for fit, possibly mil standard considerations and so forth, we have a nice ideal solution for aerospace. We offer an ergonomic cover with non-slip notches for human interface. And again, we've got to keep the package as small as possible so that we don't disrupt that environment and try and maintain that feel that the pilot is used to having in a non-equipped or non-measured situation. The miniature aspect of something like this is extremely important. For anything that involves the human interface, whether it's the pedal measurement we talked about previously, or in this case the joystick measurement, it's important that we keep the environment as close to the original environment so that the pilot has the same comfort level. So we have to take those kind of things into consideration. So in this case, you're looking at a relatively compact solution that is multi-component to give us that XY measurement. All right, let's leave our atmosphere for a few minutes and talk about something that I find extremely exciting. That's the Mars Rover Curiosity. As I mentioned earlier, we had this tremendous opportunity to work with NASA on this project, and if anything exemplifies what we've been talking about as far as credentials, as far as proprietary issues, certainly, and working together, our design team with their design team, the Curiosity probably is the best example of that. They were looking for a supplier that could provide a multi-component solution. And if we go to the next slide where we talk about some of the key aspects, what they were looking for, obviously the environment is extremely difficult, so cryogenics factored in. We had to have a device that would withstand the Martian environment. What they were looking for was a load cell component of this device for drill head supervision and precision measurement as they would drill into the Martian surface. There were some key objectives to this. One was to prevent excessive wear and tear on the drill. Obviously, in this situation, servicing and supporting is out of the question. They had to have something with a high natural frequency so they would get the proper response. And of course, lightweight factors in. As we all know, payload and getting these things out of our atmosphere and away from our Mother Earth is extremely costly, and it's all weight driven. So this has been a wonderful experience for us. We have had tremendous success with this. And you go to the next slide again, where we show the actual rover at work doing a little bit of drilling there. We're approaching, or we're at our 1-year anniversary for the program, and everything has so far worked just fantastically. So we're very proud of our team and what they did and how they worked so closely with the NASA folks. But just to kind of summarize on the next slide, what was involved in this, we had cryogenics, as I mentioned. Of course, you're also dealing with vacuum, and that's something that is important when it comes to the outgassing issue we talked about previously. Multi-component. In the most generic application in a lab, multi-component has its own challenges, and then we throw in some of these other aspects of cryogenics and vacuum, it gets even more challenging. So, the sensor was responsible for the rover's drilling arm, for the robotic maneuvering as the thing was retrieving the samples and doing the analysis. We had to design for a relatively small size, as you can well imagine. We had to get into some very limited envelopes and spaces. And again, the working range or load to size and weight were all critical for this application. So I think this represents probably the best of all our applications, covering our design effort, our credentials, and things like that. So we have been very excited about this program, and obviously if you've been on our website, you'll see that we've been very promotional when it comes to the Curiosity. Okay, well, as exciting as Mars is, let's return back to Earth for a minute and take a look at some other applications that we've been involved with over the years. Again, this is another good example of a standard product that has been modified and built specifically for military and or aerospace applications. We have our seatbelt load cell, which is intended for just that, strap testing. In this case, we're looking at parachute testing, and of course, the most precious cargo there is are human beings. In this case, what's very specific here, there's a lot of aspects that affect the measurement and making sure we do it correctly. So when we get involved with an application like this, we're going to request that the user send us their material so we can actually test in our lab, the exact material that we're involved with in this application, because the variance in material type, the variance in thickness, variance in width can all affect that load application. So it's important that we calibrate accordingly. But these type of products involve not only human beings, but it could also involve strap testing for cargo, things of that nature. And if we go to our next slide, we take a look at our little sensor, some of the key aspects, and a lot of this evolves with working with the client, but we have aerospace grade material that we use for these applications or for this particular product. Once again, lightweight is a strong consideration because we're dealing with applications where weight factors in on almost everything, and of course small size, compact design, very critical for these types of applications. So some of the key aspects to this particular product and others that we've mentioned is, first of all, we do have a standard product that's used in general industry for seatbelt testing, things of that nature. So we already have a basis for solving the problem. Now we take this standard product, and here's a good example, and make some changes, do some customizing potentially to adapt to, in this case, an aerospace application where we're doing parachute testing, and working closely with the client, we can then tailor fit this device specifically for their application. So we have standard product platform to start with, and then with our years of experience in aerospace, we come up with the optimum solution. All right, moving on to our next application. And again, I just want to emphasize to the audience that our objective in reviewing some of these applications is to give you some exposure to some of the work that we have performed, that we actually have a track record, a proven track record of aerospace type applications, and have worked very closely with those entities to provide great solutions. With the retirement of the space shuttle, we move on to the Orion project, and we've had some involvement with the Orion payload testing. So when you look at the slide here, what we want to just kind of emphasize in this case is there are a number of different ways to get to the right answer as far as product selection. When the program started, they were looking at possibly the LCM rod end style, but they were also considering the donut style or the LTH series. And both products, perfectly good products as far as capability in making the measurement. A lot of it had to do with what I call interface or fixturing, as to how you interface the sensor into, in this case, the capsule and the chute mechanisms. With a rod end, you have to take into account extraneous forces. Being a longer type load cell, it's more susceptible to bending and moments, things of that nature. You don't have those kind of issues with the donut load cell. With a donut load cell, you have to be a little careful. You are loading in a compression mode typically, and your surfaces have to be nice, flat, and parallel. So again, we had a test here that they wanted to perform as they were doing the design and development for the chutes, and we finally came to the conclusion that the LTH series was going to be the best solution for this application. Again, size was critical, getting it into a very confined space, making a very good measurement, all things that came into play. But if we take a look at both of these products, and again we want to emphasize that we've got standard products that meet this footprint, but then we take that platform and then we go into other considerations as far as mil standards and other rigid requirements that these kind of aerospace applications demand. But in the case of the LCM family, again, miniature size, Bidirectional. It's a universal load cell, so I can measure tension compression quite easily. I have a multitude of thread options I can pick from, and in this form factor I can offer anything from 25 pounds up to 700,000 pounds, so I've got tremendous coverage on load range. If I compare that to my LTH family, I've got a much smaller package to work with. The nice thing about the donut is you have a lot of flexibility in OD-ID configurations. Now, there is a relationship in working range, performance specs or specifications, and that OD-ID height combination. So within the realm of the physics that drives that design, we do have a lot of flexibility. We still have to maintain a certain relationship between OD, ID, and height in order to maintain certain linearity capabilities. But we take this platform, and then from there we take into account extreme temperatures, possibly some vacuum considerations, things like that, and then we build, working with their team, a custom solution that fits their needs. I just want to wrap up the parachute deployment discussion with something that probably is the most important aspect of any of this, in that many of these applications for parachute development and deployment testing are safety related. And so when you look at the assets involved for our military, there's nothing more important than the safety of the crew. So when you think about, if we kind of recap from the beginning, our standards that we meet, and we look at performance requirements, and we look at all of the design criteria that go into these solutions for these types of tests, when safety does factor in, it becomes so important to make sure that you do it right and that you're giving the end user something that they can definitely count on when you're putting people's lives into the equation. Moving on from parachute deployment testing, I'd like to take us through some controls aspects of the aircraft itself. One of the more common applications, if we look at our aircraft jet yoke control, is just that, the classic control in the cockpit. And when you look at that, obviously we're back to a multi-component solution where we're looking at the force of Z and the moment about Z. And the other thing that factors in to this application, just like the joystick, is in simulation as well as actual aircraft, there's a very rigid criteria that you can't change the environment. So once again, we're looking at product requirement. In this case, we're talking about our MTA, where we have a very limited size envelope that's available to us. We have high performance to consider. Environmentally, in this case, we're not concerned about the cryogenics, we're not concerned about any of those kind of things, but performance is going to be key. So small size and performance are going to be a driver here. So once again, if we move to the next slide, where we talk about the product itself, we have a standard product. If you look on our website, you'll find this product that we offer and that we stock in a generic format. But some of the key aspects for this sensor, of course, as I mentioned, bidirectional, very small, which is going to be a requirement for this application. And we offer ranges in the force axes from 50 pounds to 500 pounds, torque from 50 inch-pounds to 500 inch-pounds. But then we take the base design, and usually in something like this, as a classic example for aerospace application, it's going to be performance and reliability. This thing has to deliver performance capabilities consistently, and has to do it for very long periods of time. And so now we take again our design team, plug them in with their design team, and come up with a solution that meets or exceeds the customer's expectation. As we move into our last application, I'm going to have to take you back up into space, which is certainly probably our more glamorous environment of all these applications we've discussed today. But wanted to just talk a little bit here about the National Polar Orbiting Project. Now, this is a satellite that's involved in weather applications. In fact, this was the satellite, my understanding, that gave us the images during Hurricane Sandy last year that devastated the East Coast. But basically, and we do want to take, I guess, an opportunity to thank the Meteorological Satellite Studies Group for providing these particular images. Without them, we would not have these, so we're very grateful for their cooperation. But basically what we have is an instrument here that's known as a Visible Infrared Imaging Radiometer Suite. Looking at the next slide for the satellite, basically what was involved here is FUTEK had to design 2 cryogenic load cells to operate down to minus 300 degrees. In the setup and installation of the cryoradiator, there were some problems in previous systems where the force being applied during the setup was incorrect. So the FUTEK solution provided Raytheon with a method to do proper installation, make certain that the installation adjustments and setup were done properly, and the load cells actually stay with the device and are in orbit as we speak. So if we look at the last slide associated with this particular application, what were some of the criteria and demands that we had to look at in order to provide a solution for Raytheon? Well, first of all, it was a custom solution, so we didn't have the platform necessarily like we had in some of the applications we looked at previously. We had to have dual bridge, and that was for redundancy considerations. Obviously cryogenic, we're working in space, so we're dealing with those temperature extremes again. Shock and vibration. Most of that deals with, obviously, the launch. We've got to be able to survive the launch and continue to work once we're up in space. And then being in space, we're vacuum rated again. And in so many vacuum rated applications, whether it's in a chamber here on Earth or whether it's in a space rated situation, outgassing again is a very key consideration. So once again, our team in close proximity to their team, discussing all the details associated with this, very important. And then of course we have to pass flight inspection. So it's probably one of the better examples of where possibly we didn't have a particular mil-spec qualified device, but we looked at what specs were required, we designed and built to those requirements, and then the end user in this case would then do qualifications on the entire system, of which we were a component. As we conclude our applications, I'd like to just kind of do a summary and take a look at what I believe are the key takeaways for this discussion today. And that is when you're doing your vendor assessment, you're choosing a vendor for this important project that has significant importance. What should we be looking at? Well, just to kind of summarize what we've talked about, you need to find somebody who's got extensive experience and a proven track record in both test and measurement ground testing, as I call it, as well as flight qualified applications. And in looking at FUTEK, we've got 25 years of history, and as you can see, we've only covered a few applications. We've got the application history and the engineering talent to provide those kind of things. The engineering talent is extremely important. You need to have a team that you work with, that you can trust, that by looking at their credentials, by talking to them ahead of time about what programs have they been involved in, you develop a confidence level that these guys are the right team for your program. I think looking at standard product offering is very important. When you do look at our products as an example, as you saw today, many of those are the base platform for the custom solution that we end up with, and that's very important. A very broad product offering is critical. In our case, besides the multitude of load cell form factors that we deal with, we're also multi-component, and I think that's an important reference for evaluation of your potential supplier. Back to the standards and the compliance, probably the first thing you want to look at is, do these guys have the quality standards and the manufacturing expertise to provide the support and get to the solution that you're going to need in your application. So those are kind of the key takeaways that I think you need to look at. And I know it's been a long webinar, and I understand that probably some of you have got things to move on to, and I want to take this time to thank everybody for taking time out from your busy schedule today to attend our webinar. And if you do have any questions, please feel free to take that into the next step. We're going to open this up for question and answer, and anything that we can do to support you, please let us know.
Our first question has two parts. The first part being, what is the operating temperature for your products? And the second part is, how well do they perform in rapid changing environments?
Great question. Typical standard compensated range. There's two temperature specifications that you look at for any strain gauge type device. One is the compensated temperature, and this would be the temperature where we're actually compensating the sensor to minimize the temperature effect on zero and minimize the temperature effect on span, so that we stay within the specifications that we publish. And the whole idea here is that you want a load cell that's measuring force. You want it to change with force. You don't want it to change with temperature. So you want that effect to be minimal. That temperature range is going to be, say, typically something like plus 60 degrees F to 160. And then the second component of that is a safe operating temperature, which, as an example, might be something like minus 40 F to plus 250 degrees F, where the sensor might not perform to the published spec outside the 6160 example, but it's a safe operating temperature for that product. The second part of the question involves temperature gradient, and that's a very important aspect to temperature compensation. The strain gauges and the temperature compensation components are located basically in the center of the load cell. So what has to happen for that temperature compensation component, which is a resistive element, to make the correction, it has to be at the elevated temperature. So if we have a temperature gradient across the body of the load cell, where, say, one end is 250 degrees and yet the center is still at 70, we haven't done enough temperature soaking to allow the temperature compensation resistors to correct for that change in temperature. So for the temperature compensation components to do their job, we need to bring the entire sensor up to or down to the new temperature. In the case of cryogenic applications, what's really occurring here is extended temperature compensation down to these cold temperatures. And again, what we're after here is a sensor that's going to give a good measurement for force or a good measurement for torque, or possibly both, and minimal effect on the zero and minimal effect on the span. So we're going to temperature compensate that thing from, let's say, room down to minus 300. So that is the key aspect to cryogenic tolerance.
John, you mentioned space rating. Can you clarify what this means?
Space rated is probably a good example in this whole aerospace discussion of where we are going to partner up with the end user, and we're going to design and build a sensor to meet cryogenic standards or conditions, also shock and vibration, and certainly vacuum. Those are probably going to be the key components to a space-rated device that, when we're done with our part, the user is going to incorporate our sensor into their system and do some additional testing to make sure that the whole system is space-rated. As far as differences compared to, let's say, commercial product, you're back to extreme temperatures, vacuum environment, and usually shock and vibration are your key components. That, coupled with high reliability. So now we get into the quality question or the quality program. Our standard quality system is quite rigid, and we're a very quality focused organization. But when we get into the build and the calibration of aerospace products, especially for a space rated application, now you get into some of these other certifications that we have that are requirements to make sure that you've got the performance and you've got the quality standards in place for a space rated product.
Next question we have is, can I take a regular standard product and use it in a vacuum environment?
Actually, the answer is yes, if you don't have concerns about outgassing. In a general application, and I've had applications where I just happened to be inside a vacuum chamber, there were no concerns about outgassing. Outgassing is one of the key aspects. The other is the sensor design. If I have a sensor design with one active diaphragm, for example, and it's low range, I could see a significant load as a result of the differential between the ambient vacuum and the inside pressure, which was sealed at ambient at the time. In which case I might just simply drill a hole. I don't care about outgassing, and I've got a workable solution. However, for most of these research applications, aerospace applications and so forth, normally outgassing is an issue, and it's a good example of why the design teams from your vendor and your design teams need to work very closely together and share information. When we ask a customer, when a customer asks us most of the time, can you build for vacuum environment? And our next question is, yes we can, but what are your outgassing specifications? Most of the time the client doesn't know, and then they have to go back and find out. And this is where that relationship comes in that's so critical, that we share all this information to make sure that we get it right. So I think the right answer here for aerospace is no, you don't want to use a standard product in a vacuum environment. You want to have us build it or have your supplier build it to a vacuum rating that has a defined spec tied to it.
Our next question would like to know the difference between piezo and strain gauge based sensors. Meaning, is one more suitable for aerospace environments?
Well, actually, both technologies have their place in various applications. I typically think, and most people do, as bonded foil strain gauge, which is our base technology, as static devices. Now, having said that, if you look at some of our miniature sensors, we have a very high dynamic range. So that's a bit of a confusing point. But piezo, on the other hand, crystal-based technology, they are designed specifically for dynamic applications. So really, when you get into making that selection, for example, gun testing, punch press work, things of that nature, very dynamic applications where you're in the microsecond arena for the event, you'd go piezo. That would be your best choice. But most applications aren't that dynamic. So your choice doesn't really come down to which technology might I use for aerospace. Your choice between the two technologies really comes down to what's my application. Am I doing something that's got a duration of 1 microsecond? I go piezo. If I'm doing something that's a millisecond or slower, I probably go strain gauge. And there are advantages to both technologies. Piezo tends to have a higher upper end temperature than bonded strain gauge. Bonded strain gauges, though, are more accurate. They have better linearity, and you've got a lot more flexibility with bonded strain gauges in your overall form factor design.
John, how many cycles can fatigue-rated sensors go through?
That's going to vary depending on a number of things. That's going to vary depending on the design, and what I mean by that is we have designs that are machine diaphragm, we have designs that are column designs, we have beam designs, and so forth, all of which have different characteristics when it comes to the number of cycles for fatigue. And the way we achieve a fatigue-rated solution or increase the cycle life is to increase the size of the basic flexure that's actually doing the movement. So conservatively, a fatigue-rated solution might be something in a particular design that could be 100 million cycles. Or, and we have had applications, for example, a pill press, where they might want 500 million cycles, and we can design for that. There are certain beam or certain flexure designs that don't lend themselves to, let's say, 500 million cycles, but there are others that do. So we'll pick one of our designs and then we'll base as a platform the solution on that. So again, fatigue rating can vary as far as number of cycles depending on the flexure design and also depending on the overall form factor of the load cell.
Does FUTEK offer radiant tolerance sensors?
This is a good example of the discussions earlier on qualifications. We do and have built sensors for radiation environments. We do not have a sensor that is radiation certified or radiation hardened. We've never had one actually sent to a lab and tested. So this is a case where we would work closely again with the client's design team, and first of all we'd have to find out what the radiation type and levels are going to be in the environment. From that we can make a determination, first of all, can we design and build something to withstand over an extended period of times in those environments. To do this, as an example, then you're using materials such as Kapton insulation, materials that are intended for these types of environments. So if the customer gives us a specification and with our experience we know we can work within that environment, we will then design and build a product that will work in his environment. If he says his radiation environment is beyond our scope, then we will obviously decline and stay away from that so that we don't disappoint our client.
John, what's the typical delivery time on aerospace-based projects?
I'd like to close the Q&A with just a couple of endorsements, and I've worked very hard not to do that during this presentation, and I hope that I haven't. The idea was to keep it generic in nature, but all of these things tie into quality. And one of the driving philosophies, or the driving philosophy at FUTEK, is our quality culture. We're going to do it, and we're going to do it right. And that is something that is across the entire product line, whether it's a standard load cell or a very specialized product like we used on the Mars Rover Curiosity. And also delivery. If we look at our metrics, and this ties into our last question, which is delivery on custom solutions for aerospace, we run 98% on-time delivery. That is both our standard product and our custom solutions, and we do that by being very precise and very controlled in the types of programs that we're involved in and how we manage those programs. And if you manage these programs as well as manage your standard product very well, you can achieve these kind of performance numbers. In terms of the availability or delivery on an aerospace product, that could vary anywhere from, say, 8 weeks if it's a rather simple request and we already have a standard product as a platform, to as extensive as, say, 40 weeks if it's a completely new build with a very complex and very demanding specification. So in any place in between. So there's no set timeline that you can use for everything. It's going to depend on how severe the application is, how complex the needs are. But what we can tell you, if FUTEK is your partner, as I said, we're going to build it right, and we're going to tell you we're going to ship in X weeks, and we will ship it on time. And once again, I want to thank everybody for your time today. We greatly appreciate you taking the time to come to our webinar. And if you do have any follow-up issues or questions, please feel free to contact us. Thank you.
Unfortunately, I think that's the last question we have time for today. I'd like to thank John for presenting all of this information to us about the aerospace industry. And I'd like to thank all of you for joining us today. As a sign of our appreciation, one lucky attendee will receive an iPad mini. To find out more information regarding the custom sensors and the applications presented, please feel free to visit FUTEK.com's Aerospace Solution page. And as always, feel free to call or email us with any questions or applications. You'll be receiving an email from GlobalSpec with a link to the on-demand version of this presentation, a PDF of the PowerPoint, an FAQ document, and the Q&A transcript. Again, thank you for taking the time to sit with us this afternoon. Take care, and we'll see you next time.